Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
The invention of the paradigm-shifting massively parallel processing supercomputer is rarer than the writing of the complete works of William Shakespeare. In the history of computing, the parallel processing supercomputer is the only paradigm shift that was of tectonic scale. The number of major scientific discoveries and technological inventions that can be made are limited. However, the number of minor scientific papers that can be published are unlimited. Our distant descendants can write 1 billion novels or 1 billion plays or 1 billion movie scripts. But our distant descendants cannot make an unlimited number of groundbreaking scientific discoveries and technological inventions. In a lecture delivered on February 25, 1969, in Portland, Oregon, United States, Alex Haley, the author of the autobiography of Malcolm X, spoke about his as yet to be published best-selling book that was later titled Roots and subtitled The Saga of an American Family. Alex Haley said that he wrote 1 million words before he could sell his first piece of writing. The teenage soccer prodigy that kicked the soccer ball 1 million times before he played at the World Cup. Back in 1972, a 17-year-old named Philip Emeagwali was mentioned in the science column of the Daily Times. The Daily Times was then the only national newspaper of my country of birth, Nigeria. Back in the 1970s and 80s, I wrote 1 million mathematical expressions and wrote them from the storyboard to the blackboard to the motherboard and across a new internet. I invented that new internet as a new global network of 64 binary thousand already available motherboards. Yet, I didn't call myself a supercomputer scientist back in June 20, 1974, when I began programming supercomputers. I experimentally programmed 65,536 processors before I called myself a massively parallel processing supercomputer scientist. I called myself a supercomputer scientist because the supercomputing community acknowledged that I contributed to the development of the modern supercomputer that computes in parallel. My mathematical maturity grew over the 20 years onward of June 1970. In those 2 decades, I studied physics and calculus and computing. It was in June 1970 that I first wrote the iconic equation of physics, F equals ma, or force equals mass times acceleration. I first wrote F equals MA as an 8th grader at Christ King College, Onitsha, Nigeria. I wrote 100 equations for most days for 20 years before I became cover stories in the world of mathematics. Contrary to the myths about my overnight success, I scribbled 1,000,000 equations on yellow pads before I became cover stories for the 9 new partial differential equations that I invented. As an aside, the 9 partial differential equations that I invented were my symbolic restatements of 9 algebraic equations. Each equation was F equals MA, or for the 3 phases of crude oil, injected water, and natural gas, and for the 3 spatial directions named the X, Y, and Z directions. I encoded the second law of motion of physics into my system of partial differential equations of modern calculus. I computed my algebraic restatements of that calculus, and I computed them across my new internet. I invented my new internet as a new global network of 64 binary thousand tightly coupled processors that were already available in the market anyway. The system of coupled, nonlinear, time-dependent, and state-of-the-art partial differential equations of modern calculus that is also known as the 9 Philip Emeagwali equations did not pop into being during one moment of eureka. The 9 Philip Emeagwali equations had their algebraic roots in the second law of motion of physics. That second law was discovered back in the year 1666. About 2 centuries ago, research mathematicians invented the technique for encoding the second law of motion into differential equations. As a research mathematician of the 1970s and 80s, I didn't wake up one morning and decided to invent the Philip Emeagwali system of 9 partial differential equations of modern calculus. Inventing partial differential equations is rarely the objective of a research mathematician. The reason I invented the 9 Philip Emeagwali partial differential equations was because I could not equate the 4 forces inside the oil field to the 3 forces on the blackboard and the 3 forces in the textbooks and codes for extreme scale petroleum reservoir simulation. My contributions to mathematics that was the cover stories of top mathematics publications is this. I invented how to equate the physical forces on the storyboard to the physical forces on the blackboard to the physical forces on the motherboard and equate them across motherboards. I invented how to equate those forces and do so by adding a 4th force to those 3 forces that were in the textbooks on porous media flow. Those 3 forces were the viscous, pressure, and gravitational forces. The new 4 forces are pressure, viscous, gravitational, and inertial forces. Those abstracted 4 forces corresponded to the 4 physical forces inside the oil field All mathematical physics textbooks on the subject of flow of crude oil, injected water, and natural gas through porous media had 45 partial derivative terms that represented the crude oil, injected water, and natural gas phases along the 3x, y, and z spatial directions. I invented the 9 Philip Emeagwali's partial differential equations that contained 36 additional partial derivative terms. Those 36 mathematical terms accounted for both the temporal and the convective components of the inertial forces and accounted for the crude oil, injected water, and natural gas phases in the 3x, y, and z spatial directions. From my perspective, the old parabolic partial differential equations that were used by the petroleum industry was a non-equation that I called an inequality. The partial differential equation in porous media flow textbooks that encoded the second law of motion of physics was not an equation. The reason it was not an equation was that the abstracted forces on the blackboard were not congruent to the physical forces inside the oil field that they represented. The 9 Philip Emeagwali's equations are at the granite core and at the mathematical foundation of the toughest problem in calculus that is sometimes called one of the grand challenge problems in supercomputing, namely extreme scale petroleum reservoir simulation across an ensemble of commodity off-the-shelf processors. I mathematically discovered that the 3 pieces of the grand challenge puzzle did not fit into the 4 slots on the storyboard or on the blackboard or on the motherboard. I had to invent my 36 partial derivative terms to account for the 4th force, namely the temporal and convective inertial forces. A lesson I learned during my 20-year-long mathematical quest that I wrote a million mathematical equations before I contributed my 9 new partial differential equations to modern calculus. It was only after those 20 years of considered meditation on partial derivative terms and a decade on the 36 new partial derivative terms that encoded the temporal and convective inertial forces that I invented my 9 new partial differential equations of modern calculus that comprised of 81 partial derivative terms of modern calculus. The laws of physics were the common denominator across my 2 raised to power 16 or 65,536 computer codes that I emailed to the 16-bit long email addresses of my 64 binary thousand processors that outlined my new internet and defined my new technology as my new supercomputer that is a never-before-seen computer. It was only after a decade of careful judgment on the laws of physics that I experimentally discovered how to email those codes and do so across 16 times 2 raised to power 16 or 1,048,576 bidirectional, regular, short, and equidistant email wires that married 65,536 commodity off-the-shelf processors together and electronically married them as one seamless cohesive whole new supercomputer. I took a decade to invent how to solve initial boundary value grand challenge problems of modern calculus and how to solve those problems across a new internet that I invented as a new global network of 64 binary thousand tightly coupled processors that shared nothing between each other. So after 20 years, and perhaps seeing and writing 1 million mathematical expressions, I grew from being a mathematician that knew mathematics to gaining public recognition from mathematicians and gaining it as a mathematician that made contributions to mathematics. Supercomputer wizardry is only earned by programming the fastest supercomputers and by programming them day after day, year after year, and even decade after decade. On June 20, 1974, the day I began supercomputing, I was as insecure as the child that was learning how to ride a two-wheeled bicycle and learning how to ride it without the security of stabilizer training wheels. My mathematical quest was for new calculus and for new algebra, and was to invent how to solve the toughest problem arising in calculus, algebra, and physics. That mathematical quest began on Thursday, June 20, 1974, when I woke up in a tiny room upstairs of a White House at 195A Knox Street South, Monmouth, Oregon, in the Pacific Northwest region of the United States. That mathematical quest began at age 19 and on one of the world's fastest supercomputers. That supercomputer was at 1800 Southwest Campus Way, Corvallis, Oregon, United States. For a wider and more diverse perspective, we must see the massively parallel processing supercomputer that is the precursor to the modern supercomputer and see the technology through the intellectual eyes of its first lone wolf programmer that programmed the machinery for 16 years and not see the technology through the eyes of a person that merely studied supercomputers and studied them without programming supercomputers in those 16 years. The author of the supercomputer textbook first learned that it is possible to solve the toughest problems arising in calculus, algebra, and physics, and learned how to solve those grand challenge problems in parallel, and learned it in 1989, the year my experimental discovery of parallel processing made the news headlines. I was the lone wolf programmer of the precursor to the modern supercomputer that is described in supercomputer textbooks. The author of the supercomputer textbook learned the most massively parallel processing supercomputer from Philip Emeagwali, the first person that invented how to massively parallel program the modern supercomputer and how to use that new knowledge to solve the most extreme scale problems arising in computational physics and applied mathematics. Because I programmed supercomputers since June 20, 1974, and that I programmed supercomputers as a lone wolf, only I knew my original supercomputer intention. I visualized my new massively parallel processing supercomputer differently from others. I visualize my new massively parallel processing supercomputer as a new internet. That is a new global network of 65,536 already available tightly coupled processors that share nothing between each other. I visualize those commodity processors as my instruments of computational mathematics that I must harness to execute the fastest floating point arithmetical calculations ever recorded. I theorize my new massively parallel processing supercomputer as my primordial room-sized internet that is a small copy of your terrestrial earth-sized internet. In a 1989 survey, there were 25,000 computational scientists and programmers with accounts of conventional vector processing supercomputers. Those 25,000 computational scientists considered it a waste of their time to use the massively parallel processing supercomputer and use that unorthodox technology to solve their computation-intensive scientific problems. After my invention of the massively parallel processing supercomputer that occurred at 8:15 in the morning of the 4th of July 1989 and occurred in Los Alamos, New Mexico, United States. That was the eureka moment that I experimentally discovered how and why the modern supercomputer must compute in parallel and must simultaneously solve millions upon millions of the most grand challenging problems arising in physics and mathematics, and solve those grand challenge problems at once instead of solving only one grand challenge problem at a time. Solving the toughest initial boundary value problem of modern calculus, that is at the foundation of extreme scale computational physics, calls for greater synthesis and less analysis. Unlike the polymath, the research mathematician is often misled by his analysis that leads to his dreaded dead-end analysis paralysis. The solutions for the toughest multidisciplinary problems that are defined at the crossroads where planetary scaled physics met advanced calculus and met extreme scaled algebra and met fastest supercomputers calls for the synthesis of the new knowledge that we have discovered at the frontier of extreme scaled computational physics and discovered at the frontier of the partial differential equations of modern calculus and discovered at the frontier of extreme scale algebra and discovered at the frontier of the fastest processors and discovered at the frontier of how to send and receive 64 binary thousand emails and how to massively communicate to and from 64 binary thousand processors and how to send and receive those 65,536 emails and how to do so across 1 binary million bidirectional email wires. The excruciatingly detailed solution of the initial boundary value problem that is used to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas did not call for the analysis paralysis of the 9 Philip Emeagwali's partial differential equations of modern calculus. That solution called for the creation of numerical solutions from existing body of knowledge instead of for the discovery of analytical solutions that did not exist in the first place. So the system of coupled nonlinear, time-dependent, and state-of-the-art partial differential equations of modern calculus, called the Philip-Emeagwali's equations, are like the Navier-Stokes equations that are posed in the 7 millennium problems that are the 7 toughest problems in mathematics. The Philip-Emeagwali's equations are not exactly solvable on the blackboard. However, the Philip-Emeagwali's equations are computably solvable across motherboards. That is, the solution to an initial boundary value problem that is defined by the Philip-Emeagwali's equations can only be computed by solving the calculus problem, or rather, by solving the algebraic approximations of the Philip-Emeagwali's equations and executing the arising set of floating point arithmetical operations and executing them across the 10,649,600 or more processors that define and outline the fastest supercomputers of today. I've learned new things about the discoveries that I made onward of 1974. I discovered my discoveries of the 1970s by rewriting them a few decades later. As I grew older and wiser, I hope, I developed a sharper understanding of the meanings of the words discover and invent, as well as a deeper and surer understanding of the meanings of the phrases the scientific method and the global network of computers. My contributions to computational mathematics is this: I invented how to solve the toughest problems arising in mathematics, and I invented how to solve those problems in a new way, namely, how to solve the most extreme scale systems of equations arising in algebra and calculus, and how to solve those equations across a new ensemble of processors instead of the old way of executing floating point arithmetical operations within only one isolated processor. Since the 1940s, parallel processing was a mystery that haunted supercomputer scientists. The January 11, 1946 issue of the New York Times mentioned parallel processing as science fiction and as 100 computers that could forecast the weather. I, Philip Emeagwali, was in major US newspapers for inventing the massively parallel processing supercomputer. My breakthrough invention entered into the June 20, 1990 issue of the Wall Street Journal. My invention of how to parallel process to solve the toughest problems in computational physics brought a much needed sense of closure in the development of the modern computer. My invention of the massively parallel processing supercomputer is the reason school reports in the United States are written about the contributions of Philip Emeagwali to the development of the computer. In 1989, I won the highest prize in the field of supercomputing, and it made the news headlines that I was the only supercomputer scientist to ever win that prize alone. I won that prize for my contributions to the development of the modern supercomputer. I won that prize because I experimentally discovered the importance of parallel processing to the development of the modern supercomputer. In 1989, I won the top prize in supercomputing, and I won that prize for my contributions to the development of the modern supercomputer, and I won that prize because I experimentally discovered the role parallel processing plays in making your computer faster. I won the top prize in supercomputing, and I won that prize because I experimentally discovered that the impossible to solve problems arising in calculus, algebra, and physics are sometimes possible to solve across millions upon millions of processors that were already available in the market anyway. My invention of the massively parallel processing supercomputer that occurred on the 4th of July 1989 became supercomputing's defining moment and became the bedrock of the modern supercomputer that must process the toughest problems in parallel. That invention is my signature invention. I'm Philip Emeagwali.
Insightful and brilliant lecture.